We're going to look at ways now to use simultaneous equations in circuit analysis. There are three ways for solving simultaneous equations, and they're the algebraic substitution, the determinant method, and using a calculator. So we're going to look at the algebraic substitution. Solving by substitution, you can solve two or three simultaneous equations in standard form using algebraic substitution by first solving one of the variables in terms of the other. So it's sometimes called solving one in terms of the other. However, because the process can become quite lengthy, we'll restrict this method to second-order equations. Consider the following set of simultaneous equations. So we've got two equations. They've been put in standard form. How can you tell that? Well, column 1 here is all the x1 terms. Column 2 is all the x sub 2 terms. And then column B is our constants. So step 1 says we're going to solve x1 in terms of x2 in equation 1. Okay, so we've got equation 1 set up so that we've moved all of the other terms to the right side of the equation and left the x sub 1 term on the left. So by going through then and dividing through by 2, we now have a substitute for x1 for equation 2. So x sub 1 is equal to 4 minus 3x sub 2. So if we substitute that result for x1 into equation 2 and now solve for as x sub 2, we end up with this process. So 3x sub 1 plus 6x sub 2 is equal to 2, just as written. Now I'm going to substitute the 4 minus 3x sub 2 for x sub 1 in that relationship. So now what I need to do is I need to expand this by multiplying through. So 3 times 4, 3 times 3 gives me 12, and minus 9x sub 2 plus 6x sub 2 equals 2. So now I've got two constants that I can move around and try to get x sub 2 on one side of the equation. So I'm going to move the 12 to the right side of the equation, so I have minus 10, and when I subtract 6x sub 2 from minus 9, I get minus 3x sub 2. So minus 3x sub 2 is equal to minus 10, or x sub 2 then is equal to minus 10 divided by 3. Cancels out the negative signs, I get 3.33. So if I substitute the value now of x sub 2 back into x sub 1 in step 1, so x sub 1 now is, and we just start from right here, 4 minus 3x sub 2 is equal to 4 minus 3 times 3.33, which is 4 minus 9.99, which is essentially 10, gives me minus 5.99. So we've just manipulated the equations trying to get common terms so that we can solve one in terms of the other. Okay. All right, so now we move into an area that you probably haven't seen before, and it's solving simultaneous equations in circuit analysis using something called the determinant. And the determinant, again, is just another process. It can be a very lengthy process, but it is nonetheless a process. It's really great for matrices that get larger than a 2 by 2. So the determinant method is a part of matrix algebra and provides a cookbook approach for solving simultaneous equations with 2 or 3 variables. A matrix is an array of numbers, and a determinant is effectively the solution to a matrix, resulting in a specific value. Second-order determinants are used for 2 variables. Third-order determinants are used for 3 variables. So everything that you see here on this page is a second-order 2 by 2 matrix. The equations must be in standard form for the solution. So the first thing you have to do, depending on how you get the equations initially, is you have to put them in standard form. So to illustrate the determinant method for second order equations, we'll find the values I sub 2 and I sub 1. The following two equations are expressed in standard form. The coefficients are the resistance values in ohms. The constants are the voltage value. So that's how we set this up. So we've got some ohmic value times some current value, which is going to give us a voltage. So first, we form the characteristic determinant from the matrix of the coefficients of the unknown currents. The first column in the determinant consists of coefficients from I sub 1. The second column consists of coefficients of I sub 2. And we can see that here, column 1, column 2. So the resulting determinant then looks like this when we extract those coefficients. So the first step is we multiply the first number in the first column by the second number in the right column. You can see what we're doing here. It's this times this to start with, which gives us 40. The second step then is this times this. And what we do between the two is we subtract them. So it's this times this minus this times this. Okay? So subtract the product of step 2 from the product of step 1, and we get a value of 30. Okay? So that gives us our first determinant. Okay, so this difference is the value of the characteristic determinant, 30 in this case. Next, replace the coefficients of column I sub 1 in the first column of the characteristic determinant with the constants, the fixed numbers, on the right side and the equations to form another determinant. So we're going to do the same thing again. So we've taken the 15 and the 8, we've removed what was in column 1, replaced it with the 15 and the 8, and we do the same thing. So this times this minus this times this gives us 60 minus 40, or 20. So this is the value of this determinant is 20. Now we're going to solve I1 by dividing the I sub 1 determinant by the characteristic determinant as follows. So you can see we put the little determinant in the numerator for the first set. We go back over here. We've got the determinant for the second set, and that was 20 divided by 30, which gives us 0.667 amps. Okay. To find I sub 2, then, we form another determinant by subtracting the constants on the right side. Okay, so you can see we've put the constants in the I2 slot. And we do the same thing. Okay, we're going to do this times this minus this times this. We subtract them, and we end up with 80 minus 30 divided by the determinant 30, the characteristic determinant, and we get 1.67 amps. So this is the same way as we've done with our substitutions, solving one in terms of another, but it's a methodical approach that you can use, and there are actually programs out there that do this. You can program your spreadsheet in Excel to do the same thing. So simultaneous equations solving by determinants. So when we come back, we'll take a look at this example.